You guys don't mind my opinions, do you?
No.
Quantum loops is a loopy theory, literally. You'll see what I mean. Quantum loops is really new. I really know absolutely nothing about quantum loops. I've read a little bit about it. Most of what I got here is out of the Lee Smolin's book, Quantum Gravity. Three Roads to Quantum Gravity. I think quantum gravity is a load anyhow, so yeah. It should be the loads to quantum gravity. His arguments are here very circular. He assumes something and says he's not assuming anything, then proves everything according to assumption. Yeah. And the arguments he's making about some things are actually 200-300 years old. If he'd ever studied history of philosophy of science, he realizes this ain't nothing new. But you'll see what I mean as I go through this. I tried to take some notes and actually be prepared. So let's work along with this and see how it goes. And I swore I'd never read out of a book to students, but I am going to read some quotes here because they're just too outlandish to really be of any use anywhere in the world. Now let's see how they can base it. Quantum loop theory is basically physics without doing physics. They can't make, you've got the quantum, which is discrete, and you have relativity, which is continuous. And you can't turn something, you can't make something continuous out of something discrete. In other words, you can't make a continuous space by putting particles together, because you're always going to have some kind of space between the particles. But that's actually what they're trying to do here. So the best thing to do in all this is to get rid of the concept of particles totally. So quantum gravity seems to be based on no matter, as far as I can tell from what Lee Smolin is stating. That really, he says that the universe is made of two, I don't want to say two things, but I'll say two things in parentheses. It's made out of processes and things. Things, particles, processes, the physical laws. So, what they're trying to do with quantum gravity, with the quantum loop theory to explain quantum gravity, since they can't bring relativity into it, they're getting rid of things. So there basically is no such thing as matter. It's all processes. So everything is processes. So I guess the physical laws exist without anything, material points or anything to hook the physical laws to.
Is that cat in the box kind of thing? Like reality?
No, this is the no cat in the no box. This is the no cat in the no box, I guess. The arguments here, do you want me to read you some of the comments on the side of the page here? Like shit. See if I have a couple other colloquial things here. Bullshit, you have to get down to a level where 2 points are not touching. You know, I got comments like, you can read my comments if you want to. I put in pencil so I can erase them in case anyone wants to flag. Those are the kind of comments I have. The arguments, he's making philosophical arguments and drawing. Well, what's a philosophical argument? A philosophical argument is a process. So there is no such thing as physics, it's all just philosophy in the way it was 2,000 years ago. But gee, then he's talking about processes, and what are processes? Change. That was either an Anaximander or an Anaximenes back around 500 BC, who said, reality is just change and nothing else. Then there's Zeno, who proved there wasn't motion. The motion is impossible. And that's sort of what this guy's trying to do all over again. I just don't understand. But anyhow, basically what he is saying is, you cannot unify general relativity and quantum theory because general relativity, GR, has background independence. General relativity is background independent, which is another way of saying everything's relative. There's no fixed, no absolute space. But he's giving it this whole new meaning and calling it background independence. He can't use the words that are normally used. He's saying everything is relative. That's background independent. But he says, then he goes on to say, quantum theory is background dependent. In other words, it's not relative, it's absolute. And it's hooked to points in space. Actual points in space, locations. But with general relativity, locations depend on each other. So if you got rid of all the particles in the universe, you still wouldn't have any space. Well, that's absolute space. I don't know why they can't call it absolute space. That's what it's been called for 600 years. But they say it's background independent. And because of this, you can't unify general relativity and quantum theory. So the only way to unify them is somehow, since he assumes that quantum theory is more fundamental than general relativity, he says the only way to unify them is to make quantum theory background independent. So it doesn't depend on points in space. But he's sort of going against the tide, because by saying that general relativity is background independent where quantum theory is background dependent, all of a sudden means quantum theory is actually the classical theory, because that Newtonian theory was background dependent. He says that quantum theory depends too much on Newtonian theory. But the quantum theorists say that the general relativity people are the ones that are actually doing classical physics. He's like trying to turn the whole world up on top of his head or something.
Isn't the very nature of quantum theory
Indeterminate.
Yeah.
Yeah. But he's somehow he's getting rid of determinism. He's not even talking, I don't even think he had the word indeterminate or determinate in the book when he's talking about it. Now he talks about causality. He talks about causality, and he takes the concept of a light cone. Do you remember the concept of a light cone? And he tries to put general relativity into terms of causality and light cones without calling them light cones. And so he draws this light cone like this. Here's a present point, and here's a light cone. The lines in the light cone represent the speed of light. So if something is over here, if I have another object over here, this is event A, and this is event B. Two different events. You represent each event by a light cone. And then these two light cones don't intersect. So there's no way, because like if this sends out a signal at the speed of light, the signal's going to go along here, and light signal going through here and there will never reach here. So these two events, or these two different people, have no knowledge of each other. But he says no, that general relativity isn't about light cones and things like that. He says this is causality. These have nothing to do with the speed of light or anything. These are causality. These are causality cones. I'm trying to explain this. It's like super weird. He says that, let me give up here a minute. There is an illusion that, this is a quote from him, there is an illusion that the world consists of objects, and the objects that they consist of are behind many of the constructs of classical science. But these objects are actually illusions. There is no such thing as a real material object. If we look at me, I'm a real material object here. But I'm not really here. I'm a process. Because if you look at me over time as a light cone, I'm not here. I'm somewhere in here. So I'm actually a process of movement, and you just happen to be slow. We happen to be slowing things down, so I seem like a real physical object right now. But I'm not a real physical object. I'm actually a movement, a process that's ongoing. So if you look here an hour later, if we look at the whole time over here, and it's causally linked, that I'm a process too. I don't have any material reality. I'm not a thing. I'm just a process that has been slowed down in your perception so that I appear to be a real physical material object. Got that?
Got it.
And we are causally linked together because this is my light cone, and these are your light cones here, and all of our light cones intersect up here. This is you in the past, that's you in the past, that's me in the past. All of our light cones link up right here, so we're right here as a process moving on. So we're all causally linked because part of our light cones intersect.
Entanglement.
So we can, well, not entanglement, but similar type idea. He doesn't even use the word entanglement either. So we're all just processes. We're not really here. What I explained to you in a minute, he spends 2 chapters explaining this. Okay, I'll go on, I'll try. There are only processes. We're just these processes that are ongoing. Slow down to where we seem to be, we're illusions that we're objects. Okay, now this means that the universe is not relative and it's not quantum. It is relational. So we live in a relational universe. And the relations are the processes that are going on. And when our light cones intersect like this, because they're causally linked with each other, that's when the relationships are, the events that happen. I love this. By the word relational was used by Leibniz. So that's another idea that's 300 years old, but Smolin doesn't seem to know that. It's like he's redoing Mach, that all the physical laws aren't about nature, they're about our perceptions of nature. That was 150 years ago. He's redoing all these philosophical things people have been doing for hundreds of years and trying to base a new theory on it. The theory being quantum loop theory. Now, in the relational universe, all the properties of the universe are described in terms of relationships between the events. The most important relationship between 2 events is causality. That, one, so I go, that's an event. And then if you're within hearing shot, eventually this is me going and then the speed of sound goes up here. So every event is the cause of numerous other events happening as the energies and everything become mixed up together. And they form relationships, and that makes the universe. So the universe is just a bunch of interlinked processes.
Butterfly effect.
Now the causal future of some event consists of all the events that it could send information to via light and other means, sound or whatever. There is no structures. There is no such thing as space-time. There is no such thing as space-time, but instead a causal structure of geometry, or a causal structure because geometry is only a metaphor. Now try and tell that to your geometry teacher, that geometry is nothing but a metaphor because space-time doesn't exist. Because space-time, go back to basic physics, you need 2 material objects, right, to have a relative position. So since the objects don't exist, they're only processes, making the decision or whatever of relative space, that relationship is reality, the objects aren't real. So therefore there can't be any geometry, it's just a metaphor. I don't know, haven't convinced you guys yet, have I?
So then from our perceptions, we could conceivably create anything if we could wrap our mind around it.
Well, he doesn't go that far.
Well, you'd have to.
But he's in a
If
sense,
everything's a metaphor and there is no distance, then I should be able to think myself to Jupiter if I really believe it.
well,
Because I'm just a process. And Jupiter's
he's,
right next to me.
he's using all these philosophical arguments to show that space-time that doesn't exist is just a metaphor. Basically, he's saying when he says space-time doesn't exist, what he's saying is it can't be continuous. Because he's going to come up in a little while and it's basically all going to be matrix, like the movie. It's this big matrix. And he does compare it to computers. I'll get to that in a little while too. No, there are a lot of problems. I'm having fun with this simply because I think it's so ludicrous. So you're already picking out some of the points where it seems even more ludicrous than I am thinking of. Now, let me see. Elementary particles are not static objects, just sitting there, but processes carrying little bits of information between them. So particles aren't really particles, they're just transmitters of information. So the important thing, besides relationships can't exist unless there's information being shared. So the important thing here is information. I think this guy's been reading too many computer science fiction stories. Because, hey, we're just programming a big computer somewhere. It sounds like this worked really good in the movie Matrix. Let me see. My note on this is escapism. Can't answer a question, so deny it exists. Deny. Okay. Well, let me see. The processes carrying little bits of information between events at which they interact, giving rise to new processes. So the processes have baby processes when information arises from a different process. They are, you'll like this especially. They are much more like elementary operations in a computer than traditional pictures of actual reality. I tell you. Now, somehow, he then moves on to black holes. I'm skipping a chapter here because I really couldn't understand it. Now, I'm trying to pick out the best. I just covered 3 chapters, guys. That's all I could pick out of 3 chapters that almost made sense.
See, it gets to a point where he gets practical applications for his...
Yeah, black holes. That's what I'm getting. Black holes are the problem. Now, he contends, and some other people contend, that black holes are where it's at. That the only way to unify quantum theory and general relativity, and I will agree with them to some point on this, is in a black hole. Now, black holes are what?
Singularity.
It's a singularity. Singularity is the actual mathematical term. Singularity means that it's infinite. They go to infinite. It's an infinitely steep curve, an infinitely steep curvature in space. But it's predicted by general relativity, correct? Predicted by general relativity. And they're predicted by GR, general relativity, and Einstein didn't even believe in them, but in the past 10 years we've actually been taking pictures of black holes, because what happens is when matter spins into, forms a spiral and spins in, the matter speeds up, and before it reaches the event horizon, it starts throwing off X-rays, and so we see X-ray bursts and other things. And then if the black hole is spinning, we can tell when they're spinning, because then if it's spinning this way, it shoots out jets of X-rays like this, and we've actually got pictures from the Hubble Space Telescope of the jets of particles being shot out like that. They're quite beautiful. You see this disk with nothing in the center, a disk of light with nothing in the center, but 2 spikes coming out like axles on a wheel. They've got photographs of them. So we know that they exist now. Einstein did not like the idea of black holes. He thought it was a travesty on God or something. But his theory predicted it, and they haven't discovered them. Now, the problem is that here's your black hole, and now here you have something called the event horizon. And anything falling into this is 2-dimensional, but remember, this is a spherical surface. So it's not a line, it's actually a surface. Anything that touches that surface gets sucked into the black hole, light and everything. That's why it's called a black hole. It actually absorbs light, doesn't give anything off. So classically, we think of black holes as what? A big vacuum cleaner sucking everything in, nothing gets out. Whoa, that's not quite true, it seems. Because if we apply thermodynamics to them and the concept of entropy, we find out that black holes give off heat. Thermodynamically, they have to come in line with the second law of thermodynamics. That entropy always increases. Because basically these would be extremely orderly, right? If all the particles and everything are located in there, and the whole universe as a whole increases in entropy. If something gets sucked in here, there's something outside that has to increase in disorder to compensate for it. So essentially, basically, what they're doing is they're causing more entropy, increase in entropy in the rest of the universe. But if they're increasing more entropy out here, in other words, this is so orderly that if a particle falls in here, it has to mean the disorderliness of particles outside there have to be 10 or 20 times greater, and that 10 or 20 times greater is interpreted as what? But what is kinetic energy at a molecular level? Heat. So therefore, they must be giving off heat. And the theory now is that black holes actually evaporate. It's called black hole evaporation. That's Hawking. That has nothing to do with quantum theory. But he's using all this stuff. Now, since he's talking about information, they're trying to develop a quantum theory to describe what happens to black hole. Because a black hole is singularity in general relativity, so general relativity can't say anything about what is happening inside the event horizon. So they're using quantum theory to try and describe what is happening inside the event horizon. So everyone thinks that this type of singularity is where quantum theory and general relativity are going to come together. They're half right. What is the other type of singularity? There are two types of singularities. Well, three, including the Big Bang. I'm excluding the Big Bang as a singularity. What are the other two types? Besides the Big Bang, what are your singularities in physics?
Black hole and the cell.
Black hole and what else?
The cell.
The cell?
Or not the cell,
The nucleus, right. The nucleus is essentially a singularity. I believe the singularity will be the point where quantum and relativity are combined. But they got the wrong singularity. It's going to be the nucleus of the atom where quantum and relativity come together. And that's what I'm trying to do. They've got the right idea, they've got the wrong application. So, and I can argue this point on about 10 different levels. But you guys can't argue it back, so I'm not going to bother. Now, I mentioned things that have you read, I've got the chapter for my doctoral dissertation on the physics of this, and I actually talk about the black hole singularity as opposed to the nucleus singularity. So if you want to go to, that's one of the papers on the net. Fingers, toes, and a nose on your face. That's the title of the paper on the internet. It's on the discs that I gave you too, so you've got that. And I explain about black holes and differences, singularities, a little bit there, not a whole lot, a little bit there. Now, let me see. Basically then, black holes swallow information. Now, information is more or less the matter of the universe. Instead of having matter and relativity, basically he has information, matter disappears, and you have information instead. And instead of having relativity, that disappears and you have processes. So, quantum loop theory is based not on matter and relativity, but on information and processes. They replace the two. So basically then a black hole sucks information. Big time. I don't know what they mean by information. In the book I've got on a sideline, please define what you mean by information. He never really says. But I can make a guess at what he assumes is information. Can anybody make a guess what he assumes information is? Well, it's quantum theory, right? Heisenberg uncertainty principle. Information would be the location and the momentum of the particle. If you remember classical physics, every particle can be represented by its location and its velocity. If you know its location and velocity, if you know, going all the way back to Laplace, the Laplacian universe, where Napoleon asks him to explain Newton's theory, and he says, well, give me the position and the velocity of every particle in the universe, and I can predict the whole future. That's Newtonian causality. So basically, the information that's lost is information we don't know its position, we don't know its velocity inside here. So that's the information. And he's basically saying every material particle, my interpretation of what he's saying, every material particle is actually 2 bits of information. Bits, B-I-T, just like computers. This is a binary system. So if a particle falls in here, an elementary particle falls in here, this has just swallowed 2 bits of information. To hell with the matter. It's the information that counts, because we're talking about that.
So the particle is actually information about the particle that doesn't exist.
It sounds rather circular to me, but that's what I'm gathering here. The process is important, not the matter, the material thing. But he's almost saying that the material thing disappears.
Right.
That he
But
sometimes
then
he
how
acts
would
as
you have a
if,
location if you had no matter? Or space-time?
I don't know. I'm not going to get into that. You're making the same arguments I'm making on the sidelines here, right? That's why I say, please define information. That's actually one of my little sideline notes here, because he never really says. I'm only assuming that's what he means, because he's talking about bits of information rather than material particles. And since it's quantum theory, I'm assuming it's that. Or either that or energy or time, the other form of Heisenberg uncertainty principle. Now, then he goes on, he talks about objectivity. Part of the problem with physics has always been what? The separation of mind and matter. This actually goes back to Plato and these guys. The mind and matter are simple. Mind is what? Religion. Religion, mind, concepts of mind and life and things like that were left to religion. And then physics and science always talk about matter. Well, this gives rise to subjectivity and objectivity. You know, in science, we try to be as objective about everything as possible. We try to separate ourselves from the experiment as if we can. But when you get down to quantum level, you can't separate yourself from the experiment. You're trying to conduct an experiment, but the problem of measurement, there always has to be consciousness present. So the consciousness making the measurement, the quantum measurement up here, according to Heisenberg uncertainty principle, collapsing the state vector, the wave function, is actually part of the system. So what he does next is he redefines objectivity to fit this new process-oriented relational universe. Basically, he wants to get rid of subjectivity without getting rid of subjectivity, so he calls it objectivity. And, well, the ideal of objectivity is, if I test, say, Newton's law of gravity, and I am absolutely objective about it, then you would all discover the same law if you didn't know it beforehand. And if something's truly objective, everybody in the universe would discover that same law. So he's saying that objectivity, though our present understanding of objectivity is that the universe, the actual physical laws we discover, are part of the universe, not part of our mind, looking at the universe. That any sentient being who discovered physical laws would discover the same physical laws because they're being objective and we're being objective and separating ourselves from the system tested. Okay? So that's the way he says it is classically. But now he's trying to change that, and he says his definition, and this is, he says objectivity is not knowable by all. So it's not that anybody discovering the laws of gravitation would get the same laws of gravitation. And he calls this a weaker form of objectivity. And he states as all those observers who are in a position to ascertain the truth or falsity of some observation would agree with one another. That is objectivity. So he's saying more or less a relative objectivity, whereas the classical objectivity is where all sentient beings in the universe would discover the same laws of gravity. He is saying basically that only you and I, if I develop a law of physics right here, we'd all come up with the same laws of physics here. But if there's somebody over on the other side of the universe who we have no way of contacting, then they wouldn't necessarily come up with the same laws of physics that we do.
That's going to do what a relative morality did for morals.
Well,
It's tear it apart until there's nothing that's true.
This is where our light cones have to intersect. I said before we can have a causal relationship between our processes and therefore share the same future. But now you separated that to the whole concept of objectivity and subjectivity. Which in essence is saying that our physical laws aren't truly universal. That the universal law of gravitation can't be universal because there's no guarantee that somebody will get the same universal.
My truth is my truth, and your truth could be your truth.
Yeah. He's carrying a fine.
Think about the light cones. If you take two light cones, it doesn't matter where they are, what location.
Yeah.
Just by their very nature, how they spread out, eventually they're going to intersect.
Yeah.
Always.
Yeah.
And he's saying they're completely separate. They'll never intersect.
He says there are cases where they never would.
That
And-
doesn't make any sense.
Well,
Because a cone is constantly spreading out. It don't matter how far
Well-
apart they are, they're eventually going to intersect.
what he's saying basically is there are blank spots in the universe where we can't communicate. Now, what will one of those blank spots be where we can't communicate?
Black hole.
Black hole's one. Yeah, the black hole's one. Then he goes on and says, but the black hole in a sense is universal because we can all see the black hole. And the event horizon is a universal, truly universal thing because we can all measure the same event horizon from any point of view. It's getting heavy here. I didn't bring my boots. Now, he then throws out Einstein's equivalent principle, which is the basis of all general relativity. Do you remember the equivalence principle? Einstein did it in 1912.
Is that with the scale?
Yeah, I'll explain it briefly again. That is basically, if you knock me out and throw me in a totally enclosed room, the only way I know I'm on the earth, is if I'm standing on a scale and I have my true weight. But without any communication between me and the rest of the universe, no windows or anything, I may not be on the earth. I may be in a rocket out in empty space accelerating at 9.8 meters per second squared. So there's no way to tell whether the acceleration is due to gravity or due to a rocket engine. That's the principle of equivalence. And that allowed Einstein then to make the transition from a four-dimensional space-time to general relativity, the principle of equivalence. It seems that's not really true, according to him. Because you can tell the difference between the two, and it has nothing to do with gravity and acceleration and weight. What does it have to do with? It has to do with temperature. If you take two people accelerating at the same rate, A and A, one person is accelerating at the rate A in a vacuum. No nearby matter. And the other person is accelerating at another place in space with nearby matter. They have no contact. They can't see where they're at or anything else. They have no way of knowing whether they're either near matter or in a total vacuum in an empty space with no matter nearby. That's the equivalence principle. But if they have thermometers in their spaceship, they can tell whether they're near matter or not near matter. Because according to the law of thermodynamics, at least the way he is interpreting it, let me see. If you're accelerating in a vacuum, your thermometer would not change because there's nothing outside. The temperature is a measure of random motion, right? Random motion of your gas, whatever. But in empty space, there's nothing to give. There's no random motion in empty space, total vacuum, so there's nothing to give a non-zero temperature. So therefore, there's nothing relative to which, in other words, your temperature would be relative to your spaceship and not relative to outside the spaceship, because there's nothing outside the spaceship to be relative to. But if you're accelerating at A through a gas or something, and I'm not talking about this is not anything about molecules bouncing off. This has nothing to do with friction or anything like that. This is just a general concept of space. You would actually see an extremely slight change in temperature here, because the temperature of the matter outside that you're accelerating through, or past, your temperature would be relative to that, so you'd actually see an extremely small temperature change here. In other words, the temperature outside is absolute zero, but there's nothing relative to measure this relative to absolute zero. But outside, even if all the matter was at absolute zero, it would be measuring absolute zero outside, so therefore your thermometer would show the difference between absolute zero outside and inside. Here it can't show the difference between absolute zero outside and inside because there's nothing outside. It sounds hokey to me. I'm just these were quotes I hit. Now what they derived then is that temperature is proportional to acceleration. And therefore, he just threw out the equivalence principle. It may work for gravity and acceleration, but it doesn't work according to thermodynamics. Thermodynamics says there is no equivalence principle, according to what he's saying here. I don't buy it, but
What is the quantum loop?
well, that's I'm trying to get to. This is all working up. This is all working up to the quantum loop.
I'm like, wait a minute.
This is all working up to the quantum loop. In fact, they actually give it a formula. It's not just temperature is proportional to acceleration, but temperature is equal to acceleration times h with a little bar over it, over 2 pi times the speed of light. Now what this implies, what all this implies is that there's something called a quantum fluctuation in the vacuum is implied by all this. It is the quantum fluctuation that gives you the randomness that you can measure the temperature and makes the temperature proportional to the acceleration. So that is called a quantum fluctuation in the vacuum. Don't feel bad if you don't really get all this. It took him 30 years to. He's talking about all these different people who are adding little bits to this logical argument. Now, this implies two whole new laws of physics, which I'm going to read out of the book. Sorry. This implies two whole new laws of physics. One is called Unruh's law, U-N-R-U-H. That's a person's name. It's not a comment. Unruh's law. And it says that accelerating observers see themselves as embedded in gas of hot photons at a temperature proportional to their acceleration. That's this. Even if you're flying through the vacuum, these quantum fluctuations in the vacuum would give you the reading of temperature in your spaceship, rather than actual fluctuations in position of actual particles. They would be due to the quantum fluctuation. Then there's Bekenstein's law. With every horizon that forms a boundary separating an observer from a region which is hidden from them, boundary which separates an observer from a region hidden from them. Got that? That's the event horizon he's talking about. There is associated an entropy which measures the amount of information that is hidden behind the boundary. Yeah, that's the amount of information that's swallowed by the black hole.
So that's where he's talking about the heat coming out of that.
Yeah, it's just quantum fluctuation. That's the heat coming out. The heat coming out is absorbed. It can't be heat in the form of particle moving and bouncing around. kinetic energy, like you said. The heat coming out is, the heat that's being lost, that's being evaporated from the black hole, is actually the quantum fluctuation in the vacuum. That's where that heat's going. Not the moved particles or anything like that. Let me see. There's associated entropy, which measures the amount of information which is hidden behind it. This entropy is always proportional to the area of the horizon. Aha! We have something to go on here. The amount of information, you've got information going into the black hole. Position, momentum of the particles that are being swallowed. Or if it's swallowing photons, maybe their energy is the information. But everything would have at least 2 bits of information. So every time something that doesn't really exist falls in there, it is information. The information is processes. So if we look at the information loss, we're doing the processes, which is quantum loop theory. And if we look at the particle being lost, we're just doing old-time general relativity and quantum theory. So it's the information going through here. But the amount of information swallowed here is proportional to the surface area of the event horizon. So now we've got the amount of information swallowed is proportional to the surface area of the event horizon. Remember, like I said, that's not a circle, that's a sphere. It's a three-dimensional object. So, we can't measure how big, we don't know how big the actual black hole is, because all of our theories fall apart there. But the event horizon, the surface area of the event horizon, is measurable. And by his definition of objectivity, it is objective to anyone who does it. So therefore, everyone would measure the same event horizon. So the event horizon is like an absolute thing, because it's perfectly objective, measurable by everybody, and proportional to the amount of the information lost in it.
Is it the only absolute in this theory?
Well, it's not absolute over time. It's just that if different people are looking at it, they should get measured the same. Because it's going to be fluctuating, and as more matter, shrinking, as more information. As it loses, as it evaporates, then it's going to get smaller. So it's absolute only absolute in the sense that different people would measure, if they all measure the same time, they get the same reading, which is his definition of objectivity. Now, I can't read my own writing. The area of the horizon, therefore, is proportional to the square of the mass. The information is proportional to the surface area of the event horizon. Then, by logical argument, the surface area then is proportional to the square of the mass inside. And we're measuring in Planck units. We're measuring in Plancks, planks of wood. No, in terms of Planck's constant. Now, therefore, the entropy is proportional to the surface area. The entropy, if you remember, is S, is proportional to the surface area. Therefore, we can measure the entropy of the black hole, which means we have information. You see, we can't have any information. None of our theories cover in there, except thermodynamics. But now we can tell you how much entropy there is in a black hole. I'll get to what all this implies. I'm almost aware of it. I've gone through a whole page of notes. I'm only down to half a page of notes now. The entropy in a black hole is 1/4 of the surface area divided by Planck's constant, Planck's constant measurement-wise, times the universal gravitational constant, G. So we know what that is. Now what this entropy is this is a measure of the amount of information that has been sucked up by the black hole. So now we know how much information has been sucked up by the black hole. Now this leads to Hawking's law, Stephen Hawking, that the temperature of the black hole is equal to K over M, where M is the mass of the black hole, and K is a specific constant. And then therefore this radiates heat out, and you get the black hole evaporation. But that means there's information being lost by the black hole. So what happens to the information that's being lost by the black hole? Since this is radiating out heat, that means the entropy is changing. So that means that the black hole is losing information. Now that's a big rub. That actually has nothing to do with quantum theory, because Stephen Hawking isn't doing quantum loop theory, and he's been talking about this for a long time, all this information stuff. And basically, is this information lost to the universe? In other words, is the universe getting dumber because black holes are sucking up information? I'm putting it in simple terms.
Makes sense.
Didn't
So
he
that's
just didn't he just
anti-entropy.
use the bet over that?
What?
Stephen Hawking?
He has bets with Penrose and a couple
I
other
think I
guys.
read a couple weeks ago, he just lost the bet over that, whether the black hole actually loses this information. Because he
Was that with Kip Thorne?
might have been.
I think that was with Kip Thorne, who's a
Yeah.
general relativity
Because he thought
specialist.
the information was lost and this other guy didn't.
Yeah.
I guess the other guy won the bet.
But see, this is all tied in together. They may not be working quantum loop theory.
Right.
This is actually fairly standard modern physics here, because this Hawking and Penrose and everybody's doing this. It's just how Lee Smolin puts it together to get his quantum loop theory. Now, what the heck does all this mean? Well, it means they're developing a quantum theory of the black hole. Now, what Lee Smolin and others claimed this implies is that there's a certain informational limit to the universe. There's an informational limit to the universe. Now, they're searching for the meaning of temperature or the search for the meaning of temperature and the entropy of a black hole is now leading to the discovery of the atomic structure of space and time. That Lee Smolin and others believe that this implies that there are atoms of space and atoms of time. They claim that this proves, big time proves, that space and time are not continuous. That there are atoms of space and time. So,
Non-existent atoms.
yeah, process atoms. Now, what it comes out is that they've actually, if we look at not the black hole, but the spherical event horizon around it, that if we could look at this event horizon, actually it's a little tiny patchwork matrix of space and time. So if we can look at it small enough, what we'd see is like a fabric, squares like that. And I believe I read in there somewhere, but I couldn't find it when I was trying to get ready for this lecture, that it's a little patchwork like this. And as I remember, I'm pretty sure that each side here is 2 Planck lengths. So that's 2 Plancks, 2 Plancks. So these are like little squares, 2 Planck lengths. A Planck length is 10 to the minus 36 meters. Okay? You got that? So this is like a little matrix or fabric, and that's what constitutes space and time, is this little fabric here. 2 Planck lengths on the side, right? And what's between? What's inside that little thing right there? He claims this is all this stuff I told you implies the truth of this. Now, what is in there, inside the matrix?
Space atoms.
No. No thing. I can't say nothing, because nothing would imply a vacuum, which is continuous space. But there's not even continuous space inside there, so there is no thing in there. That these little lines are space, make up space. And so these little squares, like, or cubes, or how many ever dimensions you want to have, are the actual fabric of space and time. Now, this is the only way that they can make quantum theory background independent, is going through all this stuff like this, so that you can combine it with general relativity. Now, let me see. It says go to page 102. What the heck is on page 102? More garbage. See, you can see all my comments along the side. See all my scribbling on the side of the pages? This is where it's getting hot and heavy. Now,
So are gravity and time atoms made out of nucleuses?
no. When I say atomic, I just mean it can be broken down to the smallest unit.
Oh, okay.
This is the smallest unit. I
That
don't
was
mean
really-
atomic in that sense. This is the smallest unit of space and time. And I'm pretty sure he had the two Planck lengths on the side, which would be 2 times 10 to the minus 36 meters on each side. But I couldn't find that when I was looking through it before class. I read this like about 4 or 5 weeks ago. So, this raises 2 profound questions. Is there an atomic structure to the geometry of space and time so that the entropy of the black hole could be understood in exactly the same way that entropy of matter is understood, as a measure of information about the motion of atoms? This is all implying this lattice network. Actually, not a matrix, but a lattice network. The other question is, when we understand the atomic structure of geometry, will it be obvious why the area of the horizon is proportional to the amount of information it hides? So it's like he's turning what I just told you around backwards and asking these questions and answering these. He said all this started developing in the mid-1970s. I never heard of it until, a couple years ago, but it's supposedly been developing since mid-1970s. Now, a black hole whose horizon has a finite mass can only hold a finite amount of information, because the amount of information is proportional to the surface area. Therefore, if it has a finite surface area, it has a finite amount of information, therefore it cannot be a mathematical singularity anymore. Because the mathematical singularity is an infinity, but it's not infinite, it's finite. So when we look at black holes sucking information, it's no longer a mathematical singularity, an infinity. So we can actually use it for doing calculations. The greatest amount of information that can be stored behind this is 10 to the 66 bits of information per centimeter squared. Now that's actually on the event horizon. So if you look, since it's a two-dimensional surface, you look at this, as in each little centimeter by centimeter square of this lattice he's talking about, you'd have 10 to the 66 bits of information. So if we knew the whole surface area, we could actually calculate how much information, limit of the information stored in there, according to this theory. And he claims that is testable. They're looking for a black hole to test this. I'm not sure exactly how they're going to do it, but they're trying to find a good black hole that we can go up and say, count all these little bits of information. Somehow. There's some type of experimental test when they find the correct black hole. Now, this boundary to how much information can be stored in a black hole is called Bekenstein's boundary, after that Bekenstein's law that I read to you in a minute. Now, therefore, because of this, because of this limit to how much storage could be in the surface area, that implies continuity is impossible. Because this implies that we can only go so far. See, like this would be a bit of information. This square would be a bit of information right there. So if there's a finite amount of information that can be stored as proportional surface area, then that implies a small scale structure to space and time. Because if there's no limit to the amount of information, it would mean that the space and time in the surface are continuous, because you keep on going down, 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 infinitesimally small. So it's this thing that implies this lattice structure to space and time. And this is all calculated through that entropy, calculating out that S is equal to 1/4 h bar over hg. So this implies, so therefore, continuity is impossible. This is an argument I had when I was one physicist on my doctoral committee, and when I was doing the thesis defense, he swore up and down that there is no such thing as a point. Although he wasn't working with any of this, he was basically essentially agreeing with this, in that space and time are not continuous. And I asked him quite simply, what happens to calculus? Because the space is not continuous, calculus is bogus. Because all the theorems of calculus depend on space being continuous. If you get really into calculus, the calculus and the upper mathematics, all the theorems are based on continuity. If there's no continuity, calculus goes out the window. So your mathematical basis is used in all these, in science, goes out the window if there isn't continuity. He couldn't answer that. I shut him up, but good, when I asked him that. He thought he was a mathematician more than a physicist. But anyhow then, a continuous space and time would imply an infinite storage of data inside the event horizon, which is impossible. Now, I won't get into the rest of it. All of a sudden he throws in quarks and quantum electrodynamics and all these other things to make a really big mess out of that. Now, this lattice is made out of something called Wilson loops. These are Wilson loops. That's where the idea of quantum loop comes from. Because these little lattice sections are called Wilson loops. He calls them Wilson's loops. Then later on he calls them Wilson and Polyakov's loops. So Wilson is one invented, but some guy named Polyakov made advanced a new theorem about them. So they're either Wilson loops or Wilson and Polyakov loops. And these are the loops in lattice. Now, basically then, he calls this an evolving spin network, because this has something to do with the spin of particles. You know, half spin, one spin, things like that. I don't know where it comes in, but let me see. When you bring in quantum theory and everything, let me try and draw this. He has a drawing of the Wilson loops like this. He's got a 6x5 square. Okay, that's a little section of space, the lattice of space. And he's got a point Q here, point Q there, and from this point Q right there, he goes like this. I'm trying to duplicate the drawing in the book here. Okay, up one and over one. He's got another point Q there, and then he's got Q there and Q there. So he's got a little drawing like this in the book. And it says, quarks and strings, as strings is in superstring theory, as conceived by Kenneth Wilson. Space is imagined as a lattice made of nodes connected by edges. The quarks can live only on the nodes. So, this would be a quark right there, and that would be a quark right there, and that would be a quark right there, and that would be a quark. Quark can only exist on the nodes. The strings, or quantized tubes of flux in the field, connect the quarks, but can only exist on the edges. So these would be strings. Strings lie on these edges. So that's one string between these two quarks. That's another string between those two quarks. The distance between the nodes is assumed to be finite. The distance between here and here is finite, meaning two Plancks. Two Planck lengths, I think. Either one or two Planck lengths. I couldn't find that detail in the book again. But much smaller than the size of the proton. For simplicity, the lattice shown here is drawn in 2 dimensions only. So it wouldn't be, this would actually be a 3-dimensional thing in 3-dimensional space. So instead of being little squares, they'd be little cubes. Then you could have quarks on the corners of the cube, and then on the edges of the cube would be strings. So in essence, what they're doing is basically the strings wrap around those points. Now he says that loop theory, loops are much smaller than the strings and superstring theory. String theory relies on a fixed background. In other words, superstring theory is background dependent, like old quantum theory, because string theory is developed from old quantum theory, so it's background dependent. So therefore, the strings, and this lattice is background independent because it's developed from general relativity. So therefore, the loops are more fundamental than the strings of superstring theory. So what they're trying to do is they're trying to combine loop theory and string theory into a single theory called M theory that I talked about before. That the strings actually like curl around here between quarks to make up particles and such. But the strings are bigger than the loops. And together those make literally fabric of the universe. It says space may be woven from a network of loops. That's a statement he makes. Strings can be described how they knot on the loops. So different strings for different reasons would be, this is a square knot, and that's a granny knot, and this is a Siemens knot over there, different things like that. So strings then would form different types of knots on the loops and give rise to different particles and different things that don't really exist because only processes exist. Got that?
Oh, I get it. I get what you're saying. Yeah. I don't get it.
Well, this is I don't agree with it. I think this is all a bunch of hokey shit myself. But I'm explaining the way Lee Smolin is explaining here. So basically, what they're trying to do is they're trying to take this combination of superstring theory and quantum loop theory and come up to the M theory, Moshok theory. Remember I told you what M theory really is? No one knows. You guys are some of the few people in the world who really know what M theory is. It's I think Moshok, which is the you guys weren't here. The idea of superstring theory is it's going toward a more comprehensive theory called M theory. And a friend of mine was with what's the guy's name? Bigner. The guy that Witten is the one. Witten is at Princeton. Witten is the one who came up with the idea of M theory. Well, Witten is into the Kabbalah, the Jewish mystical tradition, Kabbalah. And so he named M theory. And she was with him when he named M theory. And so she's one of the few people who knows that M stands for Moshach or something like that, which is the Jewish name of Messiah. So M theory is literally the Messiah theory. I can't remember. I think it's Moshach. But basically what Lee Smolin and the other people are saying then is if you combine the strings with this loop theory right here, then that will lead to the eventual M theory. That's a superstring theory. Because the superstring theory people realize that they don't really have the M theory. That they're saying the M theory is something beyond what they're doing. Well, now Lee Smolin is trying to say, well, you combine the M string theory with the loop theory, and then that will eventually give us the M theory. And you probably have to be a messiah to understand what they're talking about. Well, you guys wanted it. Now, this is an interesting book, but oh man, some of the logical arguments will give you headaches in it. Really. I tried to boil it down the best I could. But what this does is, with this thing of quarks on the nodes here and everything, basically this then incorporates all of quantum field theory, quantum chromodynamics, and quantum electrodynamics. They're doing it this way so they can say that this is like the heir to all these other theories. Now, there are 3 roads. The title of the book, 3 Roads to Quantum Gravity. The whole thing here is that they want to incorporate gravity into the quantum theory. So there are 3 roads to the quantum theory. Superstrings, that's one road. Quantum loops is the second road. And that's what they're trying to do. They're trying to combine the two here. The third road is the everything else theory. And he more or less implies, well, there are those individuals out there working towards quantum gravity who really, we don't know what they're doing, but goody for them. This is his opinion here. And they may come up with some really good ideas, because what happens is people out here working Never Neverland on the other third road, individually in different ways, every once in a while they come up with something good. So quantum loop theory grabs it and applies it to quantum loop theory. That's why it's taken quantum loop theory since the 1970s to develop. Because it's like, if you read the book, and he apologizes for all the people he leaves out of the book, because other people he leaves out of the book are giving important discoveries. So he's talking about guys in South America. He meets some guy in Italy. They sit together down over beer, and they have these ideas together. And then he says, hey, all that applies. And, so quantum loop theory is actually like a 30-year evolution of different ideas being incorporated. They talk about Penrose. They talk about Feynman. All these different people. Somehow Penrose's twisters get into this, and everything else. It's just pretty crazy. But what I don't like is that he claims that quantum loop theory is a development from general relativity. But general relativity is continuous, and he's chucked out the continuous. So in spite of his saying that it's developed from general relativity, that's a load of horse pucks or whatever the guy
Hockey.
matches. Horse hockey. Yeah, he used to call it. Because he's getting rid of the whole basis of general relativity, which is continuity, and he's just basically turning general relativity into another quantum theory. So what he's doing is he is ignoring three roads to or quantum gravity. But what he's doing is missing a fourth road, which is the superhighway to gravity quantum. That's the road I'm on. Since they're saying gravity will become part of the quantum, I'm saying the way Einstein originally said is that gravity theory, general relativity, will eventually explain the quantum. That Einstein's idea with unified field theory, UFT, unified field theory, was eventually the quantum would evolve out of the mathematics and continuity would remain. Now my theory, since I'm talking about our four-dimensional space-time as a thin sheet, curved in a fifth dimension, the width of the sheet, it's not a fixed thing, it's like a relative thing. So the effective width of the sheet is where you get the quantum, in my theory. It's proportional to the width of the sheet. That's where the quantum comes from in my theory. So I'm keeping true to the idea of developing quantum out of continuity. Okay? I know this was long-winded, but once again, I don't know what the hell I'm talking about up here, so it doesn't matter. Of anything I've talked about, this is the thing I know least of. Like I said, I never heard of quantum loop theory until a few years ago. And I heard of it just basically with regard to this. Now I know for a fact, everybody is looking for quantum gravity. There are people who are making all kinds of claims based on quantum gravity. I go to these consciousness conferences, and there are people saying, well, consciousness is due to quantum gravity. And they're non-physics people. They're non-physics people who don't realize there is no such thing as quantum gravity. There is no theory of quantum gravity. At best, it's a speculation at this point, because no one has been able to do it. And Lee Smolin, this book was written, I think, in 2000 or 2001. If you read that article he has in Discover, it sounds like Lee Smolin. That article in Discover magazine, October issue? Mm-hmm. That article sounds like he may be thinking that maybe this isn't going to work. That maybe quantum loops aren't going to do it. And he seems to be more relativistic in that article. Granted, it was written on the occasion of the 100th anniversary, 2005 of Einstein. But he's very kind to Einstein here in this article. You really should read that article, get it off the internet or something. Lee Smolin, October Discover magazine. But read that. He sounds like he might be getting a little bit tired of this and may not think this might be a dead end road. It's sort of implied between the lines in his article. But the only other alternative is, they've been trying for 30 years to get quantum gravity. They haven't been able to do it. They've been trying for 40 years to find the graviton. They can't do it. At some point, these guys are going to figure out they can't do it because they've got the wrong approach. The only other approach is, instead of starting from quantum and going to gravity, general relativity, starting from continuous quantum general relativity and going to the quantum. And as I said, that's the road that I and a few other people are taking. I have a contention, two contentions. One, they're right in looking at singularity to see where quantum and relativity come together. They're looking at the wrong singularity. That's one. The other is that you can't take something discrete and make a continuity out of something that is discrete. Because if you take two discrete things, put them together, there's always going to be some empty space between them. And that empty space means that they are relative, continuous. However, you can take a continuity and turn a continuity into discrete things. In other words, you can't take something large and make something smaller, but you can't take something smaller and make something larger. Therefore, continuity and general relativity are more fundamental than quantum. And I'll start on that note next week.